Thanks for that introduction, Jan, and hi everyone who's watching. Beautiful day here in Victoria, but I'm glad some of you have chosen to spend some time learning about what I'm doing with invasion modeling in the Antarctic. And so just a sort of quick overview of what I really mean by ecoinformatics, and it's really just sort of taking an approach to invasion modeling and biodiversity modeling in general, where we're focusing on ecological traits and the relevance of a range of different traits, be that species traits or the environment interactions, or any of these sort of principles that we're looking at, and seeing how they're actually ecologically relevant, and therefore our models are a bit more ecologically informed with the data that we're using. And so I'm going to talk about how we use this for invasion modeling, but it could still be applied to a range of different biodiversity modeling alongside that. And so in the Antarctic context, what are we using this for, and how is that sort of working to improve these models, and how are we actually applying these in that context? So we'll start with this cliche quote from George Box that all models are wrong, but some are useful. And so how are they useful in this in modeling Antarctic invasions? So they're especially useful for predicting invasions because we can vary climate variables, and we can try and predict scenarios that haven't happened yet or might not happen, or there's a probabilistic chance that they could happen, or a different scenario could happen. And from an invasion point of view, really predicting and prevention is much more cost effective and ecologically sound than waiting to see what species establish and then trying to work on an eradication program after the fact. For example, Macquarie Island, the eradication of rabbits there cost approximately 25 million Australian dollars. And so there are clear benefits of trying to get accurate predictions from models rather than trying to fix things after an invasion has happened. Generally speaking, it's quite a low risk approach, especially with regard to execution, because it's using existing data and it doesn't require us to take on too much risk in order to be able to run a model. But there are some caveats with that in terms of where do we focus our effort, and how do we actually make sure that the effort that's going in and the resources going into these models is actually useful. And then when it comes to applying the outcomes of these models, that's where the risk really starts to creep in. And so being 2020, I use COVID as an example. Early in the pandemic, there are a range of ecological niche models looking at COVID, predicting the relationship between climate and COVID infections. And because the pandemic kicked off in the Northern Hemisphere in spring, there was this argument that come summer, the climate would actually make COVID less of a problem. And that actually got picked up by quite a few governments, actually, in some countries, arguing that maybe COVID wouldn't be a problem come summer. And not understanding the ecology behind that organism really sort of was detrimental to the outcomes. And so there is a climate factor in terms of a free living virus, but we have to also consider that the virus sort of is inhabiting a vector and what the ecology of that vector is. And so rather than looking at maybe the ecological niche of a virus, we should have been looking at the ecological niche of human, which given our spread across the planet, we've done pretty well filling almost every region, regardless of the climate, and we have so many adaptations to survive. And so it's really important that we're careful with how our outcomes are used and how they're applied in the context. And when it comes to invasion modeling, the risk profile is really more, if we say a species definitely can't establish or invade an area, then that's quite a high risk scenario. Whereas if we can say, oh, there's a good chance that the species might invade, then it's a lower risk profile in terms of how we're communicating our science and trying to translate it into policy. So looking at Antarctica especially, there are a few things that could be interpreted as making it much easier to do these models, but all of these are a double-edged sword. So if we look at isolation of Antarctica is great in terms of protection because we can work with discrete units where we can establish biosecurity principles that will prevent an invasion. But at the same time, that can mean getting hold of the data that we need quite tricky, as I'll demonstrate later in the talk. The biotic simplicity, as in there are relatively few complex interactions because of the generally lower species richness across Antarctic environments, are useful in terms of we don't have to consider too much the effects that biotic interactions might have on invasions. But that also then leads to them being very unique environments, which can make it tricky to try and extrapolate what we're seeing in a species native range or another invaded range to try and translate that to Antarctica. And so a lot of the work that I'm doing is really trying to see how can we make these models more useful, especially in an Antarctic invasions context. And so looking at this classical invasion model, which sort of lays out the framework of which a species goes from an alien introduced species and then leads through to establishment and then potential spread. A lot of what I'll be talking about will be focusing on the establishment stage. So looking at what factors determine survival and even reproduction of a species. And also I'll look a little bit at the transport and introduction stage. And then the spread stage is a lot more driven by stochastic processes rather than niche processes, which are the focuses of my work. But some of the niche processes aspects that I discuss will also feed into these spread stages. And so the go-to tool that we really use in invasion modeling are the species distribution models. There's a range of different species distribution models. By definition, it's just any model that models a species distribution. But the correlative approach, which is seen as the traditional SDM, is one of the most commonly used tools in invasion biology and also looking at range expansion of species with climate change. And so there are a few problems with that, especially working in a novel environment where we're trying to project these models into a new region. And so with this very basic conceptual example, I'll just sort of highlight why that could be a problem. So say, for example, we have presence data for a species within an environmental space. This could be multiple dimensions, depending on how many environmental variables we have. We can fit a model to that and then try and predict where that species will occur or the probability of that species occurring to another region. And if we have absence data as well as presence data, then we can maybe use that to penalize the model. And the model could be a generalized linear model, it could be a GAM, there's a range of different approaches. So this is just a very simple conceptual demonstration. But then if we come to trying to predict where a species could possibly invade, more often than not, we're trying to extrapolate to an environmental variable range or an interaction between the variables that is not actually seen within the species native range or in its previously invaded range. And so with that comes a lot of uncertainty. And possibly even worse than having uncertainty in our models or predictions and understanding that uncertainty is if, for example, we had a lot of absence data because a species has never been introduced to that range, and we took that as a penalty that we'd apply to the model that says that maybe that species just doesn't survive there. But if there's no opportunity for the species to have previously invaded, then we could be making a false statement there, and that could really affect our models and extrapolating out. So say, for example, in the Antarctic context, if the species has never been introduced to a very cold environment, then any predictions we make to cold environments could be made invalid if we take that absence as something that we're training our model on. And so this has resulted in quite a lot of flack being thrown at SDMs and traditional correlative SDMs in particular, especially in terms of spatial transferability, which is what we're doing when we're trying to predict an invasion. But you'll see here from this recent study that transferability can actually be increased if we have better presence records, and we can also reduce the number of predictors in our models. And just from this figure from this Liu paper, you'll see that it's not a carte blanche across all species. There's a lot of variability in the type of organism we're modeling. And for the Antarctic context, we're especially interested in ectotherms, aquatic species and plants. And so the transferability is really important here. And so I've personally applied these models and used them to great effect in the Antarctic region. But that is acknowledging that there are some shortcomings of using these. And so I'm a firm believer that people in glass houses should not throw stones. So I just want to explicitly acknowledge that, yes, we've used this approach and there are some limitations that we discuss in our paper, but there's a lot of the things that we're doing better and continue to do better with these models in the future. So going back to this classical model, we can improve data collection, we can get much better species field observations, and we can also improve environmental data, which is one area I'll focus on in a second. And we can also improve these statistical and dynamic models by incorporating species trait data rather than fitting them purely on a correlative approach based on where species are found. And that will give us much better predictions. So one of our students, Rachel Lee, who's just finished up a PhD looking at Antarctic biodiversity in a range of different contexts, she examined what the environmental data actually look like for where we want to do this modeling. And one of the challenges she found is that with climate models and with WorldClim data, they're actually trained on temperatures at 1.2 meters above the ground, which is, for a lot of our species that we're interested in, as Sharon pointed out in her talk, not actually relevant biologically or ecologically, because the organism is actually inhabiting a much sort of lower height in the microclimate environment. And so Rachel put together these remote sense land surface temperature data sets, which was a great improvement. And she used a range of spatial and temporal gap filling processes to try and fill in any gaps from this remote sensing data that we get from cloud cover. And she was able to produce what we believe is a much more ecologically relevant data set for temperature. And this is the sort of data we'll be using in future modeling. And during that process, she also identified that WorldClim and some of the downscale climate models are very much elevation extrapolated models. And therefore, if you see here for Marion Island, the temperature that we're actually getting in from WorldClim is almost an exact mirror of elevation. Whereas if we look at the land surface remote sense data, there's a much more windward-leeward difference in Marion Island here. So she really identified that there's a challenge with using these global data sets because of how they treat downscaling and interpolation using elevation data. And to take that a next step further, we, Kath Dixon, a PhD student who recently finished up with Melody McGeoch, published this paper with Justine and Alex, as well as co-authors, where she highlighted that they measured the environmental temperature across Macquarie Island using a range of different loggers. And so we can actually use these in situ microclimate models to try and improve downscaling of remote sense data, so we can greatly improve some of the microclimate predictions that we're making for environmental variables. And this is just regards to temperature, but we can use this for a range of other environmental variables such as water temperature, as long as we are really pragmatic in what variables we're looking at. And so moving into models and how we can use trait data to try and prove these, I'm going to use Hypergastrura viatica, which is a springtail species, as an exemplar. And this species has invaded Macquarie Island and a variety of other subantarctic islands, and is basically taking over in huge mats. And as you see here, if we just fitted a correlative model looking at the native range, the model might predict that you need low temperatures for the species in order to be able to survive. And if we look at Macquarie Island, it sort of sits plonk in the middle of that range of temperatures. And so if a model fitted using purely correlative data was used, it might actually say the species couldn't survive because the minimum temperatures don't actually fit within the range. But from an ecological point of view, Macquarie Island is essentially permanent springtime, and so we'd expect the species to do really well. And so if we look at the physiology of the species, we can also identify that the critical thermal maxima, so that's the warmest temperature that the species can operate, is actually much warmer than its native range would suggest. So there is some competition going on in its native range that must be excluding this species from just taking over all temperate environments. And so understanding the physiology of the species is really going to help us with better predictive models. And we took this a step further in some work led by Luis Petiera and Jess Bartlett, looking at the larval survival of Eretmoptera murphyi, which is an invasive species which started in South Georgia and has now invaded Signy Island in the South Orkneys. And looking at the larval survival, we identified that the range the species could invade could extend to the Antarctic Peninsula. But interestingly, with climate change, we might actually end up losing some of this environment in its native range of South Georgia. And so the takeaway from this is that all we need for a great model is to have a bespoke model for each potential invader and invadable environment, which is a lot of work. And so it would be great if we could measure every single species that is a potential species to take over, and we could understand all the specific bias and uncertainty in the data collected, but it's not really practical even in a large project such as SAEF. And so I think that with better filtering of environmental areas, looking at essential variables relative to species invasions and human activity patterns, we'd be able to filter both the invadable environment list and the species lists to reduce down the number of species that we have to try and identify ecologically relevant traits, and then also possibly measure those ecologically relevant traits. And there are a range of approaches such as species agnostic modeling and looking at transport pathways that we can work on to try and distill that down to a much smaller list. In our original study in 2017, we looked at the 100 worst invasive species, but when we also looked at a cold tolerant species list, which was achieved through expert solicitation, we identified that they were much more likely to invade than some of the 100 species that were a problem elsewhere in the world, but not really for Antarctica. And so just to demonstrate very quickly how we could apply this in a marine context is that first, maybe we'd have a lot of species that we're working with. Once we identify a source, a potential invasion area, then say, for example, Hobart Harbour, then we could look specifically at the species found there. And then I propose that we emulate transport, and that is we take biofouling plates, say, for example, from Hobart Harbour, and we subject them to transport conditions and see how many species actually could survive the transport process. And that will allow us to actually quickly knock out a lot of species that could never survive transport, either under current oceanic conditions or under future conditions. And it's a really sort of pragmatic approach to try and reduce down which species we actually have to measure traits for. And then at the measurement of traits stage, we can also reduce that down based on how related some species are, and then get really specific and bespoke models for all of these invasive species, resulting in much better targeted biosecurity. And so just to wrap up, I want to highlight that species distribution models, even correlative species distribution models, do still have a use, especially when we're looking at and using the right ecological data and making sure it's relevant for the questions we're asking. And tailoring can be very resource and time intensive, but some of the filtering approaches and data pragmatism that are being used in other fields could really be readily applied here to improve things. And I think the skills within SAEF could contribute substantially to this. Thank you.